Oh, I hope if I plug that in.
I assume that's supposed to say my handwriting sucks.
Yeah. I've needed an excuse to try this. Now, I don't know that we'll actually need it, but I figured I'd bring it in the event. Yeah, my handwriting sucks, and that is emphasized by the fact that I clicked a button at some point and it created lines instead of scribbles. So I don't know. I keep putting on my list like, oh, you know, play around, because I do a lot of I have recorded a lot of lectures for other things, and sometimes like, you know, teaching biochem, it would be nice to be able to do the math, and instead of having to record myself on the board. It's okay. Nice. Yay. It's okay. All right.
You are? Are you going to be teaching biochem for next year?
Oh, so I taught it for undergrads this past. Between us and those online and anybody like and Google, who I'm sure is listening, I don't like. I can teach biochem, but I don't like teaching biochem. That is not my thing. So, but I guess if it's the difference between like, I don't know, job versus no job, I guess I would teach it. But I'd have to think really hard about it. Like, Michelle, you make good money, right?
Yeah, I'm curious if they'll ask you about teaching this summer.
So,
what time does that class start? May? Yeah.
Who taught it this past summer? Was that Dr. Gaddis? I know for this summer, as far as I know, I'm teaching cell biology again. And at some point, it feels like we are nearing the end, and I realize we're not even half.
Recording in progress.
I had a question.
Yes.
For our manuscript presentation,
Yes.
am I writing the paper and doing the PowerPoint to submit, or just the PowerPoint?
Just the PowerPoint.
Okay.
Yep. That's a good question. So I don't know if you can hear her online. She said, or she asked, for the presentation, which I will post the schedule today. I have it mapped out and I haven't done it yet. Right. So it is like you're doing, it's in the spirit of the manuscript review, except you will just tell us about what the paper was, why were they doing the study. You can kind of follow those same benchmarks that you do for the manuscript review. Instead of necessarily focusing on one figure, which it'll all depend on your paper and like how, you know, that you can take one source and it can be presented in a variety of ways depending on the needs of the person doing it. So I would say generally you'll probably aim, you don't have to show every figure and like walk us through every one, but you want to give us the story about what was their question and what were the key things that led them to their conclusion or answer. So generally that will include multiple figures, but it might be that the way they did their study or the way you're going to present it, you might just spend a lot more time on one. So there's really no, there's no right or wrong way necessarily to organize it. As far as needing to write anything, a PowerPoint is all I need. And depending on when you go, you may be giving it on Zoom or in person, or it's also true if it's an in-person day, but you just rather do it on Zoom, you can do it that way too. So I would like it if everybody can submit them beforehand, and then depending on how you present, I may load it for you, or you might just share your screen remotely. Oh yeah, that reminds me of what I was gonna say. Manuscript review 2. I think I got everybody's graded. Fantastic. They're all good. So just keep that up and you'll get all those points. I think it was Scott. Somebody made a comment and said on manuscript review 3, I don't know if you noticed, but I slipped one in that I helped study. Right? That was on purpose because I have intended to do that every semester I've done manuscript reviews because my friends are like, why aren't you making them read some of your stuff? And I was like, well, one, I don't necessarily want them reading my stuff because some of it might be bad, right? But I liked that study because it was an interesting, I did like half of it or so was what I did finishing my PhD. And then the guy who followed behind me made it worlds better than where I'd left it. And that was a cool paper. And then he has continued, or he did until he graduated, following up on that and looking at different aspects of complement and recovery, and it's super cool. And maybe one day it'll have some therapeutic stuff. Okay. Questions to have.
One more question about that as well.
Yes.
I will ask people to like put my 2 sources in discussion, and I don't know if you like have gotten to them yet.
Oh, maybe I missed them. Yeah, will you remind me when we finish? And I'll go in and I'll make sure I haven't missed anybody. And I don't think we've had any duplicates. I realize now using the discussion is a hard way for me to keep up with what's duplicated and what's not. But if we have duplicates at this point, I'm sure it'll be fun. I'll just have to compare the 2 who have the same thing against each other. Right? They get to share, was it 15 points, 100 points, whatever it is. So they have to share it. That's a good reminder, though. Okay. I had a couple of things to talk about. All right. Lost my page here. All right. While I found that, did anybody have any specific questions? So I sent and added an image from another text that I'm not sure that I ended up incorporating into any of our lectures. But I was asked, what is the difference between like the B cell receptor and the antibody, right? Like, what is the difference? Really, the difference is for one B cell, the B cell receptor is an antibody that is attached to the membrane to see antigens to activate, versus the secreted form, what we know as an antibody. That antibody is there to be secreted out to go and cause an effect to something that B cell has already been activated against. All right. I apologize for any. All right. Oh, shit. So if we were to draw, you all know how to draw the antibody. So one thing you want to do is draw it, be able to label the different parts. What that does is that helps reinforce what does it mean to be a heavy chain, and what are our different types of heavy chains? How many classes of heavy chains do we have? Oh, Jesus. Oh, real. I'll get to your thing now. Whee! This is going to be terrible. All right. So that is a skewed antibody, right? How do I know that that's an antibody? What do all antibodies have? What are these? Oh, God.
Heavy chain and light chain.
Yeah, I think I heard somebody say heavy chains and light chains. Just based on the way they're drawn, which ones are the heavy chains? Yeah, the big ones. Right? Heavy because they have more amino acids, so they move slower on a gel. I'll draw it again. Whoa. All right. So we have the light chains and we have the heavy chains. How many different variations of light chains are there? 2. What are they? Kappa, and lambda. Right? And how many variations of heavy chains do you have? 5, right? All Greek are all they are all based on Greek lettered genes, and they correspond to antibody isotypes that are the I guess Anglo-Saxon, whatever, the normal letter. IgM relates to mu chain, and A relates to alpha chain. And what's interesting that I actually probably knew but forgot, or maybe never knew, they are named such because of how fast they moved. Alpha is one that moves fairly quickly because overall when it's monomeric, it tends to be the smallest, or it can be the smallest. But we can say for certain which one is the biggest. Yeah, M is huge because M is how many antibodies all stitched together. 5 antibody molecules. There is evidence that there are cases where it's hexameric. I naively thought I would study that as a grad student, and then I thought this is dumb. Because then there was like, well, there might not be any functional significance, so we ditched it. So we have the heavy chains, the light chains. What would you name the region here? And there are going to be 2 of them, right? Yeah, your FAB, right? Fraction of antigen binding. Pretend you are standing up and you are holding your arms out, and your hands are what you can grab things with, right? That's where you're going to bind antigen. And on each heavy and each light chain, you have a particular Ig fold domain. And these give you that characteristic view where it looks like, right? And these little domains are what give us our Ig superfamilies. Oh. Apparently, if you click that button on the top, it does extra things. Yeah. So that is your Ig folded domains. And this is what gives you the superfamilies. Antibodies are a part of the Ig superfamily. So are many of the receptors and molecules we'll end up talking about. So each heavy and each light chain, they both have a variable region. Why is it named a variable region? It has CDRs in it. The amino acid sequence in those variable regions is less consistent. And then even beyond that, you have these CDR regions that form these like weird fingertip-like things at the tips of each variable region. And these CDR regions are where it's hypervariable, meaning there are constantly little mutations that occur. And that's what gives us an antibody repertoire of 10 to the 9. You can recognize a billion different antigens. And as I was preparing, so part of why we're not covering any new material today is my kids didn't go to sleep until really late last night, so I didn't finish the lecture that we were supposed to do. And we didn't need to. We have space. And so as I was preparing that, what I came across was and I wish I'd come across it sooner because it's profound. We have all of these B and T cells that can recognize 10 to the 9 different distinct structures. Do you think most of those will ever see their antigen? No, a fraction, hundreds of thousandths of a percent are likely to ever see their antigen. So why have all of that? Why have all of that diversity? Just in case, right? The whole point of the adaptive response is to be able to recognize something should it ever see it. And that's how it works. So we have these really hypervariable regions here at the tip. They change constantly. That's what gives you that ability to bind antigen and do things. You have one on the heavy and light and heavy chain, and on both sides. And both antibody binding sites or antigen binding sites recognize the same epitope. They're identical. Right? So it can bind 2 things, both of which are identical to each other. What do you call the region that is not related? And really, you can, depending on the text, you can categorize it in different places. I come from a complement background, so we care about the big stem, because that's where complement binds. So what do we call that region with the rectangle now? I like it. The FC region. See, Alex is doing some of the work for me. We have the FC region. And what does that stand for? Yeah, the crystallizable. I also like, I kind of substitute my own word, the fraction that is constant, right? Because and the reason they knew it was constant is because it crystallized. Sodium chloride crystallizes very well because all of the molecules are all the same. If you start to mix different things together, they don't pack as well. And so their crystallization properties are different. And so as they were breaking these antibodies apart, they found, oh, you know what? This region that we create with our different enzyme treatments, they all fall together in a very consistent pattern that says they're all very similar. And that's what ended up giving us knowledge that there are 5 different types of FC regions, right? Those that belong to IgG and IgM and et cetera, et cetera. Now, we've just diagrammed an antibody. Do you think we can apply basically the same structure to the Ig that is a part of the B cell receptor? Yeah, it is basically the same thing. The only difference is in the case of the membrane-bound form, one, it's going to be on a membrane, so that FC portion isn't free, it's attached to the membrane, and you're also going to have other things that are non-covalently associated with it. I don't think we've introduced those yet, but we will. These other things are not antibodies or immunoglobulins, but they're a part of that family. So a key difference is that a B cell will end up secreting antibody because it wants that antibody structure to go and bind something to cause an effect somewhere else. Antibodies in the context of the B cell receptor are there so that the B cell can be activated. Do you think, so let's say this secreted form and this membrane-bound form are on the same B cell. Do they recognize the same antigen? Identical. When a B cell gets activated, recall, it's going to do what? It's going to differentiate eventually to make plasma cells. One of the big functions of B cells is to eventually make lots of antibody. And so they're going to undergo this process of clonal expansion. So if this were the activated B cell, every time it divides, it's going to keep that exact same B cell receptor until the point that it gets to where it's producing antibody. And those antibodies will be the secreted form of the immunoglobulin that was in the B cell receptor. Identical. Now, the question was brought up, well, that's cool, but like, what about all these isotypes? How are they different? What's interesting is, let's say every time this B cell receptor is clonally expanding, it's proliferating, we know the B cell receptor is going to be identical. When we get to the point that we have plasma cells, this plasma cell could start producing IgM. And what do we recall about the secondary response? Which antibody usually predominates? Yeah, lots of IgG. It's one of the ways that for most antigens you would say, are you in a secondary response, or is it the first time you've seen an antigen? You can not estimate, you can infer that from what some antigens and their responses look. So let's say this one is producing M, and this one has gone through the process to change the types of antibody it's producing. It's no longer producing M, it's producing G. So 2 different classes of antibodies. Do you think they recognize the exact same antigen? Yeah, because they are all clonally expanded from the same B cell that was initially activated. And so we know from clonal selection that there's also a polyclonal response. Those tend to be the best. So not only do we have this antibody, or this B cell, but we have one over here and one over here. And without giving you any information, should you know that they are all going to recognize different structures, or at least different epitopes? Because in your body, naive resting B cells that have not been stimulated all bind different things. Once they activate, you will then get lots of copies of the one that got activated. And so this one could maybe bind ABC, and this one could bind BCD, and this one could bind whatever whatever the continuation of that is. Now, all of those epitopes could be on the same antigen. That's what gives you the polyclonal response. You're recognizing different parts. And that way, just as a means of redundancy, if the pathogen mutated and this B cell and its memory stuff that we'll look at in the next unit, if this B cell no longer can recognize, well, because you had so many other B cells that could, you still will probably have protection or you would still elicit a response. I feel like I'm missing something. I don't know. So the difference between secreted antibody and membrane bound in the B cell receptor, just where it is and what its purpose is for. That, and as long as they're coming from the same B cell that is being activated, they're going to have the same specificity. Now, there are other events that occur. I think we referenced, I'm pretty sure we referenced them. It's the idea that antibodies can get better at binding these hypervariable regions. Even after a B cell has been activated, they can go through what's called affinity maturation, or and more specifically, somatic hypermutation. And somatic mutations are pre-existing. It's not mutations that occur during development. It's mutations that occur once a cell is already established. And so there will be a process that will undergo in the form in the germinal centers of your secondary lymphoid tissue, and that is where these regions are going to start to undergo some more mutations. And we've already said, once a B cell is activated, that epitopic specificity never changes. So during somatic hypermutation, it's not changing what it binds, it's changing how well it binds it. So it's experiencing mutations, and if those mutations make it bind less effectively, that cell is deleted. Like that clone or that copy of the master clone is gotten rid of because it didn't bind what it was supposed to bind. And really, they only keep, during affinity maturation, you only keep the clones that have gotten better at binding. And that is why, as an adaptive immune response continues, those B cells start to bind tighter and tighter, which encourages the elimination. So we produce antibodies sooner that aren't as strong binding because you need some protection right away, even in an adaptive response. But as that adaptive response matures, the ability of these structures that are being made get more, not more specific, but they bind more strongly, which means they work better. That was a good question. Oh, I lost it. All right. Muriel asked, slide 51. Oh, your antibody kinetics. Yeah. So during the declining phases, there's still a little bit of Ig being produced. Yeah. So it's during the stationary phase of the antibody response, for every one molecule of antibody that's being secreted, you have the elimination of like one is being removed. So your net gain is 0, but you still have some being produced. During the decline phase, for every one you produce, you're losing 2 molecules. So the slope of it is you're no longer producing it, but there will still be some, or you're no longer producing lots of it, but there will still be antibodies circulating, and they're going to decay at different speeds based on what they're binding, you know, how they're binding, what's clearing them. That is a part of the contraction phase of an immune response. And this text doesn't have a chapter dedicated to it, but increasingly people are studying how immune responses resolve because that drives a lot of disease and damage. The response to, for example, people who have active tuberculosis, that can create this weird response where the bacterium is kind of under control, but the immune system just won't turn off. And so it creates lung damage because, not necessarily because the bacterium is there, but because the immune system keeps attacking even though everything's fine. That's a good question. Does somatic cell mutation happen both on the B cell? We're going to take it very cleanly. Somatic hypermutation does not happen in the B cell receptor. We'll just understand it's just a thing that happens to the antibody directly. Somatic hypermutation are events that occur once a B cell is activated. Once it's activated, the binding of the B cell receptor is going to be second to everything else. That's a good question. That's a good question. All right. I'm going to ask some questions, kind of that rapid recall style. So think in your mind, and then I'll tell you what the answer is, and then you can nod your head, I got it, or I guess thumbs up on screen. Actually, I'll draw it because I need to practice at this, so let's do that. Clear all my drawings. Okay. And they're going to be a little bit biased towards complement because I would argue that might be the thing that, since it's the most recent, it might also be the thing that's the most confusing. But before we do that, did anybody get to the complement stuff and think, man, this makes sense? It's just intuitive. The people online can't see this, but everybody in the classroom is just like fist pumping. They got it. That is the experience of most people. I would say less than 5% of people are like, yeah, complement. That makes sense. It's kind of like coagulation. It is essentially the same type of thing, and I despise I don't care, I don't like it, except that the coagulation system activates complement too. And directly, like cleaves C5 without any help. All right, let's see. Okay, we are focusing on 2 anaphytoxins. What would those 2 anaphytoxins be? I got to stop clicking on that. Dang. I think what I need to do is inactivate the buttons on the pen.
C3A and C5A.
I think somebody online maybe said B.
C3A and C5A.
C3A. Okay, yeah. So anaphytoxins are C3A and C5A. There are other molecules that get cleaved that can be inflammatory. We're gonna ignore the other things that can do that. C3A and C5A are anaphytoxins. You are all well aware of what anaphylactic shock is. Robust inflammation, hazardous to health. C3A and C5A are good at stimulating inflammation, recruiting neutrophils and activating neutrophils and recruiting lymphocytes. They are good at saying, hey, there is something wrong here. Come here. And the more you release, the more recruitment you'll get. What are our opsonins?
C3B.
So I had one on C3B. Anything else?
C4B.
C4B can act as an opsonin. Oh, yeah. And IC3B, C3D, and C3DG. Where did all of those things come from? The clue here, it's especially easy, or at least it makes it less challenging if you have the number of the complement protein still intact. That's why classical and lectin tends to be a little bit easier to navigate. IC3B, we remember, well, that has to be something related to the C3 protein. B tells us that in most cases it's cleaved and it's the bigger part and it's stuck to a membrane. And here, IC3B, it's been inactivated. And C3D is that inactivation continuing. And C3DG is just on and on and on. Now, why would we inactivate C3B? For what reason would we want to have it stop working? Because as long as there is C3B present, we can continue to activate which pathway of complement?
Active.
Yep. Or did you say alternative?
Active pathway.
Active pathway.
The classical.
We're gonna, yeah, so if we just have C3b, that is good, that is what's going to allow us to activate our alternative pathway. Our classical pathway would be that's activated mostly, or at least best illustrated by bound antibody. The lectin pathway is activated by these sugars that are sticking off on foreign surfaces. So C3b, if it's just being deposited places, it can drive alternative pathway activation, because all alternative pathway needs is just some free C3b stuck somewhere. And that's via factor B. Factor B likes to bind C3b, and then it perpetuates C3 cleavage. So why inactivate that? Because what we want to do we want to inactivate it, so we don't want any more complement activation, but do we still want the immune system to know that something is wrong here, or at least that something needs to be done about it? So it's inactivated, so no more complement activation, but it is still a sign, come clean us up or come eliminate us. And so our deposition fragments are a way for the body to say, hey, we don't need any more complement activation, but we would still like some stuff to happen that helps clear it. And especially with things like C3D and DG, those can be marks on antigens for B cells to say, oh man, this must be important, because not only did my B cell receptor see it, but another molecule on me saw that the innate system thought it was a problem too. What collection of proteins are related to the terminal pathway? Let's say we'll do this first. What does activation of the terminal pathway result in most obviously?
Soluble C5a.
So yeah, we're going to get some C5a, right? And that's our anaphytoxin from above. We activate the terminal pathway. We get some anaphytoxin. What else do we get produced? If we have C5a, what other thing do we also have?
You're talking about the membrane attack complex as well?
That's right, membrane attack complex. And that is a result of C5b stimulating the collection of C6, C7, C8, and C9. And here I'm going to put C9 with a little n, because you get many copies of C9. If you allow the MAC complex to start forming on a membrane, tons of copies of C9 are going to form this pore. And what is that going to lead to? Lysis. Yeah. It's going to, if you get enough of those, the cells, the target, whatever that target is going to burst. Let me clear this. All right. Which of our three activation pathways does C2 belong in?
Classical, alternative, and lectin.
Classical, lectin. And what's interesting about C2, it doesn't belong directly in the alternative pathway. The alternative pathway is just when C3b binds to a membrane and gets together with factor B. Oops. But the classical and the lectin pathways, although they use different proteins to initiate, they both result in the activation of C4 and then C2. So tell me which complement protein is doing the initiating in the classical pathway? C1, yeah, C1q, and when it binds, it then allows C1s or copies of C1s and C1r to come in, and they do the cleaving of the next steps. What does our lectin pathway get initiated by? Which complement protein?
MBL.
Yep, mannose binding lectin. And when it binds, it recruits homologous. Ooh, run out of space. There you go. That's MASP1 and 2, which do the same function as C1R and C1S, and that is to activate C4 and C2. Now, we think of the classical pathway by C1q binding being related to antibodies binding antigen. Could it be other things? It could be like C1 or CRP. It could be structures on apoptotic cells. So know that there are other ways for the classical pathway to get initiated, but we think of it most often as being a part of the adaptive immune response or contributing to the adaptive immune response. And that is because it requires the deposition of antibody. As an aside, which antibodies activate complement best? IgM. IgM is good. It's a good, because it's so big, it has 5 copies. It's easy for C1q to bind it. What's the other one?
IgG.
IgG. IgA is interesting because it doesn't activate complement, which you would think, hey, out there in the mucosa, why not? But it doesn't have it doesn't have FC regions that are available. But IgG is very good. And there are differences in the subtypes that I think are in the notes. But collectively, you could say IgG is good at activating complement. If I were to say, tell me what factor I does. What does factor I do?
Complement activation.
Say it again.
Did it inhibit complement activation?
Yeah, factor I it's an inhibitor. Right? Most of the way we control complement is by trying to stop it. Your body spends lots of effort producing these inhibitors that our cells are decorated with. And one of those is a soluble factor called factor I, and it's really good at cleaving the convertases. It's especially good at acting on C3b. But it needs a cofactor. Essentially, factor I is a really good machine, but it does not act unless it is shown where to act. Somebody give me an example of one of these cofactors, which are also complement inhibitors.
C4B.
So C4b would be one of its targets.
MCP.
CR1.
Yeah, MCP is a good one. Factor H. So factor H is going to be this cofactor. So if you see factor H, you should think something to do with the alternative pathway. And then you learn, oh, it's an inhibitor. So what factor H does is it interacts with the alternative pathway convertase, C3 convertase, and it starts to destabilize it, allowing factor I to come in and clip it apart. MCP is one that can help decay all of them based on what it binds. and then we have others. There is one complement inhibitor protein that doesn't help factor I work.
DAF.
Yep, DAF, the K accelerating factor. My English is bad. No help factor I. DAF works by destabilizing the convertase, but not because it just gets in the way. It's the chaperone at a middle school dance. Right. I don't know in that equation what MCP would be, but still a chaperone, but maybe a chaperone who calls the cops. I'm not sure. I'll get lost in that thread. That's not useful. All right. Um, all right. This is really something you probably already know, but I'm not sure. I don't remember doing it very well. But it's an important point to note, especially as we get into, yes, for this test, because it's the way cytokines can act. We're also going to start to see increasing examples of cytokines being used to drive adaptive cells to do things. So if we have this cell and I were to draw this, it's producing, let's say, IL-2. IL-2 is a key cytokine that drives proliferation, especially of lymphocytes. What type of messaging would this be? If I am the cell secreting it, and then it is also causing me to respond. Yeah, that's our autocrine signaling. Auto self crin signaling or something, I don't know. What about this case? This is also secreting IL-2. I had somebody online. I think I was talking over you. All right, so we're going to have paracrine signaling. And that is where one cell secretes it, and then it interacts with neighboring cells. Think local signaling. But what if blood vessel? What if this one is secreting it? And then it's going to travel in the bloodstream. It's going to go somewhere else. Say you have an inflammatory response. You stepped on a splinter, or you got a splinter. You didn't know. And what does a splinter do if you don't do something to it? It's going to get infected, right? Because splinter is a breakage of the skin. You're going to permit microbes, be they foreign or ones that just live on your skin. They're going to get access to a place they're not supposed to have. You're going to have an inflammatory response. It's going to have those 4 cardinal signs of inflammation. But what happens if that inflammatory response doesn't resolve? Right? It just keeps going. You're eventually going to notice, I don't feel good. You might experience a fever. Well, that is long-term signaling or long-distance signaling. The cells in your foot, those immune cells in your foot are secreting pyrogens like IL-1, IL-6, TNF, and they're traveling a long way to go to your hypothalamus. What type of signaling would that be? Yeah, endocrine. Or we could call it, no. I was starting to feel pretty confident because I wasn't clicking that button. So I was like, oh, I'm starting to get this. It can also be called humoral. Right? That is why your antibody response is called a humoral response, because where do those antibodies go? Into the bloodstream to go wherever they're needed. Show off. If I could navigate it to go up there to the typewriter thing, I'd do that too, but I'd be all over the place. All right, so we have that humoral response, or humoral signaling that can message it around. Now, you have, the way that we are grouping our cytokines together, I think for our purposes is intuitive. Instead of saying, okay, what is the cytokine family and learning the members and seeing the different things, instead we have them grouped by function. So tell me what some of our functions of a cytokine could be. And if you just can remember the groupings, like the title on the slide, so to speak, that's also okay too. Even more broad, because that's actually a good point. How is it that those target cells know to respond to a cytokine? What do they express? Yeah, they have to express receptors. Why is it then when you secrete insulin, your liver, or I guess I say when you secrete, insulin, why is it that all of the cells in your body don't suddenly start doing things with glucose? Because they're not expressing the insulin receptor to do anything. Same is true with cytokines. Why is it that all the cells just don't immediately start to do stuff? Because they have to express the receptor to see it. So that receptor expression is going to, and interacting with a cytokine is going to let us have some events. My favorite, because again, I'm biased to innate immunology, innate responses. IL-1. Do you all remember what the PRR that generates boatloads of IL-1 beta is called? Yeah, it's the inflammasome. We didn't talk about it, but I should have done it. Maybe next year's immunology, I'll include this paper. There's a type of cell death called pyroptosis. It is explicitly when macrophages and some other cells explode themselves to release all of the IL-1 beta they have in them. And that is in many parts caused by innate responses due to like IL-1 beta signaling. Macrophages just build so much of it, and then they get the signal to just erupt. So pyroptosis, they just spill it all out. Lots of cool stuff. I made it through college just thinking there was necrosis and apoptosis. And then there's necroptosis and pyroptosis and netosis. That's when neutrophils spill their chromosomes out to form a sticky web that traps stuff. Oh man, nature is crazy. Nature. There's a Family Guy episode where the people are watching this video and they're like, "Damn, nature, you scary." That's what I think of. So, moral of the story at this point, don't do things to annoy your immune system, I guess. All right, what else can we do? What would tie well to chapter 5? Cytokines would do well to drive, adaptive responses. We hinted at it, but a really good illustration of this, T helper 1 versus T helper 2 responses. What guides a T0 cell, or TH0, excuse me, which is just a naive, but it's a cell that's just seen its antigen, but it hasn't decided what it's going to become. And if you hit it with a particular type of cytokines, you can get different lineages, TH17, TH2, TH1, or TH7, or TH9, or Treg, or follicular helper, all these other T cell possibilities, and all of those have to do with the types of cytokines that they are responding to, which then have consequences in the cell. All right, so if you're a T0 cell, or TH0 cell, and you get IL-4, that's going to cause activation of a specific transcriptional regulator that's going to cause you to yourself produce specific cytokines to give you a response.
So if it's a TH0 and it gets the IL-4, then it turns to like the TH2.
Yeah, and we're treating, and it's true for some of these, it really can just be the presence of one cytokine. Now, in a cell, it's going to be a collection, it's a messy environment. So we are just going to think what's the most important or the one that's best characterized. So for us, IL-4 drives T helper 2 responses. Just to make nice clean lines to do it. Antibody responses. Cytokines play a role in that. The way B cells are able to mature and proliferate and how they know where to go. This is all based on the expression, the binding to of cytokines, and their chemoattractant family members. What are cytokines called that have chemoattractant properties? Yeah, chemokines. Chemokines. Are all cytokines pro-inflammatory? No, some of them inhibit inflammation. So can inhibit inflammation, and really, I could have just said inhibit immune activity, but I had to be more specific. Inhibit inflammation and adaptive responses. Because, eventually we need that immune response to stop. Chronic inflammation is never good. And if you think of it, if you've already eliminated the threat, why keep making antibodies? That is one good reason for why once we've seen an antigen, why don't we just keep tons of antibody in the blood? Because that's a waste of energy. If the threat's not there, we don't need that. So instead, what the adaptive response does is it has that memory component, right? It builds in things that can reactivate very quickly so that we're not wasting protein and energy making antibodies that we don't need at the moment. Inhibit inflammation and adaptive responses. Really good cytokine that can do this is IL-10. TGF beta. But if you were to look through the literature, you could find IL-10 being inflammatory or TGF beta driving an immune response. So again, we'll try to keep it clean. So if you see IL-10, your mind should think that's going to be an inhibitory cytokine. And so the more active a T cell response is, the more often those cells are going to start, you're going to start to see the amount of IL-10 increasing, which helps to turn it back down or slow it down. Do all T cells have the receptors for cytokines? That's a good question. So yeah, all T cells can express the receptors that would bind IL-4 versus IL-6 versus TNF. They can express them all. A lot of it has to do with how the innate system got activated. Because remember, the innate system is what forms the blueprint for how the adaptive response is probably going to go. But generally, it's thought, well, they express it all, but if there is more IL-4 available, more of your T cells are going to skew Th2. So yeah, they could respond to any of it, but there's just so much more of one particular cytokine that's where they go. Oh, yeah, I forgot. Sorry, I forgot one. I don't remember what number we were on. 6, maybe 5. I think I spelled that right. Hematopoiesis. What are some of our what is hematopoiesis?
Production of blood cells.
Yep, production of blood cells, red blood cells, and platelets. And because we're beyond the innate system, we are okay with, we can leave out red blood cells. They're important, but not that important. So we're just making white blood cells, and there are different cytokines that do that. MCSF, GCSF. In the CSF, most of these hematopoietic inducing cytokines are named for their colony stimulating factors, because what they found is that if they were to take some of these cells from a mouse and give them this molecule, they started to form these little clumps of cells. So they were inducing their proliferation. The one that doesn't follow that as well, but is a really good hematopoietic stimulating one, is IL-3. What does the IL stand for? Interleukin, right? Named so because it was seemed to be allowing leukocytes to talk. Let me make sure I got all my. I think I knocked out all the things I had circled. Yep. Right. Do I have any other questions? Is this helpful?
Can you describe an anti-antibody again?
Oh yeah, I knew somebody was gonna ask. He asked, describe anti-antibodies again. Yeah. Idiotypic antibodies, right? All right. How about to draw? I'm in the drawing mood now, so you're stuck with it. Let's see. Right. Okay, so we have an antibody. And if we were comparing an antibody that is IgA versus an IgE, what type of comparison would we be making? It'd be our isotypes. Right? What is different between them? If they're coming from the same clone, really the only thing that's different are those heavy chain regions. Now we then have an allotype. Functionally, for the purposes of this class, does the allotype matter? Why would we care? Yeah, just inheritance. Allotype is small changes in the constant regions that don't necessarily affect. So this one is circle and this one is square. The antigen binding sites could be the same, and they're also going to both be IgG. Let's call it 1. I haven't talked about that one in a while. They're both IgG1. They both bind the same antigen, but due to just the fact that mutations occur, you're going to get these small, for our purposes, insignificant mutations that allow you to track inheritance or that type of stuff. Those are allotypes. Now our last is the one that sucks, right? So it's idiotypic. It is an antibody that binds to another antibody. Is there a way to create another page? Does anybody know that? Oh, I got it. Cool. Turn down here, go up here. So in an idiotypic response, what is an idiotypic antibody going to be responding to? What part of an antibody can be different? So what I'm going to do is we're going to magnify this piece. So this is the binding cleft. And you can have an antigen here, and you can have an antigen here. And the longer you have antibodies circulating in you, those constant regions are you. Are those variable regions? They may be, right? Like your body may have seen it, but that is a hypervariable region that is just random in what generates. So it is likely that as you have antibodies circulating, your body's going to start to see those binding sites and say, oh, that might not be good, right? This is something that we're not quite familiar with. And so what will happen, idiotypic antibodies bind your antibodies, and depending on where they bind, they can inactivate or inhibit an antibody's response. For example, if an idiotypic antibody binds to this circle, that would interfere with antigen binding. Why would that be a good thing? Yeah, there's no more antigen. We don't really want that antibody just circulating around. And so by binding it and keeping it from acting, you minimize chances of an immune response or inflammation. And it's not something we talk about, but that's also how a lot of these circulating antibodies get cleared, is that they stick to other things so that they get removed. But some of these idiotypic antibodies would recognize other sequences, right? We have 1 billion possibilities of epitopes. Stands to reason one of them might be a random antigen binding region change. So in this case, if your idiotypic antibody binds over here, it might not interfere with antigen binding by our normal antibody, and nothing is of consequence. Which could be good, could be bad. So that brings up a good question that we will revisit again, but I think we've already talked about it, or at least I think you have the information to know. Has anyone ever, I don't care if you know. Do you know what happens if you get bitten by a snake and you get envenomated? So you get bit by a rattlesnake. Right, what do you usually have to go to hopefully you go to the hospital to have what done? Antivenom. And that's good, right? Like that speaks to the function of an antibody. You get these antivenoms, which are sera. Serum has lots of antibodies in it. You're getting this anti-serum that is directed against the toxin, the rattlesnake venom. So you get that and you clear it. There is a consequence sometimes with these serum infusions to treat things like that. You all have heard of serum sickness? And it is nasty. Do you know what serum sickness is? Your body is mounting an immune response to the other proteins, including the antibodies that are helping you. And often you see it like a lot of antivenoms are derived from horses. And you start to mount an immune response against the horse antibody. Right? And so serum sickness is this weird inflammatory response that's directed against the thing that's trying to help you, but it's because that thing is not you. Right? And so you see it and you respond to it, and that's why they have to treat with antivenoms carefully, depending on where it's from.
Do we develop any kind of humoral response to venoms?
To kind of beat them? Yeah, you can. So, well, to venoms, you can. So some bee stings, the reason some people are allergic is because they have a de facto IgE humoral immunity against it. Unfortunately, in the case with IgE, it binds to mast cells, and so then when they see the bee venom, they freak out and you get an allergic reaction. But there is
There's not like a helpful memory response to any of them.
you know, there can be, and they say that you can develop tolerance to some of these things, but often you see it in the context of tolerance away from an allergic, like an allergy or an inappropriate response. But it's not a venom necessarily, but that is how things like tetanus vaccinations work. You're not getting the tetanus bacterium is not what causes any problems. Well, not the big problems, but it's the fact that when the Clostridium tetani gets in you, it starts to produce this toxin, and then it causes an effect to your body. And so vaccinations against tetanus are really against the toxin, because your body will clear the bacterium eventually. It'll get rid of it, but what it can't handle is all of that toxin that's accumulating. And so you can do this artificial active immunity where you show it pieces of the toxin and it'll develop a humoral response. You could argue you could do that naturally too, just at maybe great risk, I guess. That's a good question. And we will cover that in the infectious disease chapter, which I think we'll for sure keep that one because it's relevant. But it's a good question. Oh, already answered. Okay. Anybody have any other questions? Thoughts? Cool. Well, we are done. I'll post this if it's. I'll stick it in the same place where all the rest of them go. I don't know what I'll call it, but it'll be there should you need it. And then Thursday we'll meet. I'm hopeful maybe next week we can start to do some face-to-face on Thursdays, but at least this Thursday will be on Zoom. And what we're going to cover is B cell activation, but that will